Okay, so our next batch of equations turns out that we're going to be very lucky that we do have technology, all right? Because let's go ahead and take a look at it. And what usually happens in these equations is we have a combination. In mathematics, we call things like e to the x and natural log of x, we call them transcendental functions. And then we have a transcendental function is equal to an algebraic function. So I have a quadratic equal to a transcendental. Very, very hard to solve because my x is in different locations. Here the x is up in the exponent, and here the x is being used as a base. So when we undo the other, we can't undo this guy, right? Because to get this x by itself, you can think we'd eventually take a square root, but that's not going to help out with that x. To get this x by itself, I'll apply a natural log to both sides, but that's not going to help this guy out. So no matter what we do to get one by itself, it doesn't help the other. So the algebra gets in the way. The algebraic idea for one side doesn't quite work for the other, and vice versa. Same thing here, right? To get this x by itself, I'd apply, I'd convert it to base e, but that doesn't help with that x. To get this x by itself, we'd move things around, but that doesn't help with that x. So, and then here we basically have two different competing ideas altogether, right? Here we need to convert this to a natural log. Here we need to convert this to e, but that doesn't help us get either x. So very, very hard situations. As a matter of fact, it's impossible to solve algebraically. So what we'll do is return to our calculators. So recall for our calculators what we did, we had a two-tier idea. One, we can treat this, I think method one, back in the day was to treat this as let y1 equal e to the x, let y2 equal x squared minus 2, and then we would graph both functions. So let me, without the calculator, I can give you an idea. E to the x, again, is a exponential growth curve looking like that. And then x squared minus 2, well, that's a parabola that's been shifted down, looking like so, right? And so I can see, just by putting a quick sketch together of these, I'm expecting possibly two. Right here is kind of the wild card because I'm, again, the e to the x might be going to infinity faster than the other one, but hypothetically speaking, we'll get two here, right? The other method is to move everything over and then just graph that, right? And then in this case, we're going to look for x-intercepts rather than intersections. So either way works for you. I actually prefer the x-intercept way because it's this one you can see there's some possible solutions that might get pretty hairy. They might be off my screen, but here at least I know I'm looking along the x-axis for my solution. So that's why I prefer this method. So that's what I'm going to use. So I'm going to kick everything over, go to my calculator, and in my calculator I'm going to type in, I've got my function e to the x power, and we are subtracting x squared, and we are adding 2. So when I go graph that, here's what the graph looks like, and I can see that it actually only crosses one time. All right, and so there is our solution. So this, again, I usually like you guys to show me a quick sketch of what this graph looks like. We're from -10, -10, 10 to 10, and we basically let y1 equal that expression right there. So our solution sitting right here. So to find it, I go to second calc. We're looking for a 0, right? And that's another name for an x-intercept. So I press 0. It asks for a left bound. So I'll move myself over to the left of that point of interest. So any one of these will do. Press enter. It's asking for a right bound. So I'll go to the right. And then it's asking for a guess. So that looks like a pretty good value right there. So when I press this in, it looks like x is -1.491644. And so that, right, would be the solution to that equation. So as I mentioned, right, this next intercept right here that I was anticipating didn't happen. That just means the exponential function, it's going to infinity a lot faster than the quadratic function. That's why we're not getting that. That's why it's going to infinity there, actually. All right, so there's your strategy. So nice review of, I think this is something that was an extra credit assignment many, many moons ago, and now it has a payoff because these can't be solved using a logarithmic idea or an exponential idea or algebraic ideas. All right, so we basically need technology. So the next one, again, it's not possible to solve this algebraically. I like to use the second method, so I'm going to move everything over. I have the natural log of x plus x minus 5 equals 0. So here's what I'm going to type in as my y1, and my viewing rectangle, I'm definitely going to hope I see everything on the nice standard viewing rectangle. So clear that out. Let me clear that out. So we have the natural log of x and I think I was adding x and then subtracting 5. Make sure I have that right. Yeah. So when I go graph that, here's what the graph looks like. No surprise. Notice that the domain starts from 0. That should be no surprise because that's the domain of the natural log of x. So this guy, right, limits everybody else. But we can definitely see the graph looks something like this. So we can see that there is actually a solution. Right? And so to find that solution, again, I'll use my second calc. We're looking for a 0. We do something to its left. So let me move my cursor over there. I'm definitely to the left of it. Move over to its right. So I'm definitely now to the right of that point of interest. And now I'm going to do a guess. So move my cursor, and that looks like a pretty good guess. So we're getting, in this case, x is 3.69344414. Alrighty, so there would be the solution to that equation right there, right? And again, we had to use technology. Last but not least, again, I like to kick things over. So this is e to the negative 2x minus the natural log of x, right, equals to 0. So there's my y1, and again, I'm going to graph this on my standard viewing rectangle, and hopefully that's enough. So turning to my calculator, right, we've got, we're going to clear that out. We've got our e, and it's raised to the, make sure you use the right negative, right? The negative we want to use is this negative here, not the subtraction. So negative 2x, right? And then we're going to be subtracting the natural log of x. Okay, so let's see if it has any x-intercepts. So when I graph that, all right, the graph looks like so. Okay, and we do see that there's an x-intercept. So that value, again, we find using our calculator. So second calc, we're looking for a 0. Move my cursor somewhere to the left of it. Move my cursor somewhere to the right of it. And then 0 it in on a best guess, which is about right there. And so it's getting 1.1138083. All right, and so there is how we use technology to solve some of these goofy equations. And again, there's two methods. I could have always been graphing the natural log function with the line and seeing where they intersect. Right? I could have graphed this decay model with the natural log model and seeing where they intersect. I'd have gotten the same values, but for me, it's easier to see x-intercepts and isolate my search along the x-axis. So that's why I like to move everything over and then just look for x-intercepts. So there you go. All right, so technology, nice resource. Thank goodness we have it. All right, so one more problem for 6.6. I'll do that in a video coming soon.